Encryption and authentication methods today are based on the idea that certain kinds of problems are too hard or computationally difficult for a computer to solve in a reasonable amount of time,
such as prime factorization. However, recent advances in quantum computing have raised concerns about the difficulty of these problems, because with quantum computing, information can be processed at an exponential rate compared to traditional computing. This will render current encryption methods insecure against quantum-based attacks. As a result of recent substantial development and advancement of quantum computing, a national security mandate was issued to replace existing encryption methods to make them secure against quantum computer attacks. To solve this problem, we must return to the most secure encryption approach ever invented, known as the one-time pad. It works as follows. Let's imagine two parties, Alice and Bob, want to communicate. First, they must share a truly random number which is as long as the message they want to send. It must be kept completely secret. We call this a symmetric key. To encrypt a message, Alice must convert the message into a ciphertext, where each bit of the message is combined with the corresponding bit of the symmetric key. This encrypted message can then be sent openly to Bob. To decrypt the message, Bob reverses this by using the same process with the identical symmetric key on the ciphertext. After communication, this key must be destroyed and never reused. In 1949, Claude Shannon, using information theory, proved that the one-time pad provides perfect secrecy against any attacker with unlimited computational resources, quantum or otherwise. We can summarize this with an analogy. Two people who share a symmetric key have the equivalent of a secure tunnel through which they can send one message securely against all attackers. After the message is sent, the tunnel must be destroyed until they both obtain a new shared symmetric key. The problem with this approach is it isn't practical in an online world. It requires both parties to physically share a true random number before each message is communicated. To solve this problem, Matrix 2 has created a globally patented method of sending symmetric keys continuously over the internet. This results in a secure, scalable solution to implement one-time pad encryption for peer-to-peer communication online. It works as follows. Imagine Alice and Bob need to securely communicate. To do so, they first need to request symmetric keys. The first step is to generate two truly random number sequences using a pure random number generator inside a key distribution center. We call these random sequences golden keys. These golden keys are then physically delivered to each party, and an identical copy is kept at the key distribution center. These golden keys allow for secure communication via the creation of a reusable secure communication tunnel. This provides a means for passwordless authentication as proof of identity. Once this reusable tunnel is established, the key distribution center can then generate a truly random symmetric key using a quantum random number generator. This symmetric key is sent securely to both parties through the reusable secure communication tunnel. Once each party has a shared symmetric key, they can establish a secure communication tunnel which can be used one time. For example, Alice could send Bob a message securely through this tunnel. After this message is sent, the communication tunnel between them is destroyed. If Alice now wants to send another message to Bob, they first must request new symmetric keys from the key distribution center, which can be sent securely through their respective reusable tunnel established with their golden keys. This allows Alice and Bob to communicate securely again using another one-time secure tunnel. And so this system allows the transmission of symmetric keys continuously over the internet. It's based on a globally patented method to create these reusable secure communication tunnels between the key distribution center and any number of communication parties. This results in a secure, scalable solution to implement one-time pad encryption for peer-to-peer communication online.